Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 5 of Algebraic Topology. In today's lecture, we will be concerned with what is path connectedness, and from path connectedness, we are able to define a functor from topological category to the category of sets. So before going to path connectedness, let's see what is a path. So a path in X is a continuous map from I to X. So basically, let's say this is a closed interval 0 to 1. Then a path is a continuous map from this closed interval 0 to 1 to X. And let's say this is the point A, which is equal to f of 0, and this is the point B, which is equal to f of 1. Then f is a path from A to B. Now the continuity of f suggests that this path has to be continuous. There are no breaks, and so it is just a continuous path from A to B. Okay, so we can't say that a path in X is just a subset. Okay, so it is a subset, but it is more than a subset. It is a parametrized curve inside X. So this curve, which is image of this f under this f of this set 0 to 1, is basically it has some orientation as well. So we start from this A and we go in this direction to B. So it is not just a subset of X, it comes with other structure as well. So it comes with parameterization of this curve and also some orientation. So it is more than just a subset of X. So this is how we define a path in X. So now let's see some examples of path. If our topological space is R2, we define f from I to R2 as f of t is equal to cosine pi t sine pi t. So in fact the image of f is half circle of radius 1 in R2. Okay, so let's see what is f of 0. So when t is equal to 0, cosine 0 is 1, and for t is equal to 0, sine 0 is 0. So f of 0 is 0, 1, 0. So in other words, this is the initial point. And similarly, what is f of 1? So cosine pi is minus 1 and sine pi is once again 0. So this is we can say the end point. So minus 1, 0 is the end point of this path. So as I said earlier, so we are starting from this point and we are reaching this point. So there is some sort of orientation in this curve. Now let's consider another path which is associated to this. So consider this G defined as f of 1 minus t. So in other words, just replace t with 1 minus t in the definition of f of t. So if we replace this t with 1 minus t, then we obtain this path, so which is cosine pi into 1 minus t, sine pi into 1 minus t. Now let's see what are the starting and end points of this path. Of course, since f is a continuous function, so that's why this g is also a continuous function. Now g of 0, so when we calculate g of 0, so take t is equal to 0, then we will get cosine pi and sine pi, which is equal to minus 1, 0. So in other words, the starting point of this path is basically minus 1, 0. So this point for G is the starting point minus 1, 0. Now let's see what is G of 1, that is the end point. So for t is equal to 1, 1 minus 1 is 0, so we will get cosine 0 and sine 0, so which is basically equal to 1, 0. So this point 1, 0 is the end point. So in other words, we are moving in this direction and we are approaching this point. So these two paths are different, and the only difference in these two paths is the direction. So the end point of f is the beginning point of G, and the beginning point of f is the end point of G. So that's why it is not just a subset. Okay, so if I consider this semicircle, So this path is not just this semicircle of R2, not just this subset of R2, it is more than that. It has some other structure, it has final point, beginning point, and some orientation and some direction in which we are moving from one point to the other point. So if f, in general, if f is a path in x, then f of 1 minus t is a path from b to a. So in this case, of course, as we have seen earlier in this example, that f of I is equal to g of I, because both of these represents this half circle in R2, but they have different properties as paths. Their beginning and end points are different, for example. Let's consider another example. So in this case, we take our space to be S2, which is a sphere in R3, and we define our path in the following way. So in this case, you can observe that these are points of R3, and what we have done is just divide the norm of this point with itself. So basically, dividing this point with its norm will give me a point of R3 whose magnitude is 1. And so in this case, norm of f of t is equal to 1. So what is norm of this vector? So t plus 1 square plus t plus 1 square plus t plus 1 square square root. So this is the norm or the length of this. So if I divide this point of R3 with its length, then I will get a vector whose magnitude, so a vector of R3 whose magnitude is 1. So we can say that it's a point on S2, because S2 is set of all points of R3 whose magnitude is 1, or whose distance from the origin is 1. Okay, so f of t are points of S2. Also f of t is continuous, so we can see that there is no discontinuity in this case. So it is a continuous path, and the initial point is basically 1 by square root 3, 1 by square root 3, and 1 by square root 3, and f of 1 is the final point, so it will be somewhere in the first quadrant. So let's say this is our f of 0, and let's say this is our f of 1 somewhere over there. So this is the path from f of 0 to f of 1, and this path is contained, is totally contained in the sphere S2. So what is a path connectedness? So a space X is path connected if for every AB belongs to X, there exists a path in X from A to B. So observe that this space, if I have this point A and if I have some other point B, then there is a path from A to B. Similarly, if I take this point to be X and this point to be Y, then once again there is a path from X to Y. But consider this space now. Okay, so let's say this is the point A and this is the point B. So there is a path from A to B, but it is not contained in the space. So not path connected. Okay. So similarly, if I have some point over here, let's say X, and some point over here, Y, so there is no path inside this space from X to Y. So if X is path connected, then X is connected. So consider, so the proof is very simple. So let X is path connected. We have a space which is path connected. In other words, we can find a path between any 2 points of the space, and we have to show that, X is connected. So connected means it cannot be written as union of two open sets. So on contrary, let's assume that X is disconnected. So if X is disconnected, so there exist open sets let's say u and v contain inside x such that x is equal to u union v, and u intersection v is equal to phi. So if x is disconnected, then we have this condition. In other words, x can be written as union of two open sets. So let's say this is u and this is v, and their intersection is phi. So this is our total space X. So let A be a point from u and B be a point from v. So let's say this is B. So since X is path connected, so there exists a path from A to B. So f from I to x such that f of 0 is equal to A and f of 1 is equal to B. So there is a path, but we can see that if u intersection v is phi, then there will be a gap between them, and this part of the path will not be contained in x, so which is a kind of contradiction. So let's see how to write this down mathematically. So now f of I can be written as f of I intersection with u union f of I intersected with v. Okay, so of course if f of I is contained in x and x is union of u and v and the intersection is phi, so we should be able to write it down as the following. But since u intersection v is phi, so f of I is disconnected, so which is a contradiction. Why this is a contradiction? Because f is a continuous map. So if f is a continuous map from I, which is a connected set, okay, so continuous image of a connected set is connected. So in this case we can see that continuous image of a connected set is not connected, because we can write this down as a union of two open sets which are disjoint as well. So which is a contradiction to the continuity of this f, a contradiction. So that means that our assumption is wrong and x is not disconnected. So that's what our assumption is, x is disconnected. So this assumption is wrong, and that's why x is connected. So we have proved that if x is path connected, then x is connected. So in other words, we can see that connectedness is a kind of more general thing than path connectedness. An example of a connected space which is not path connected. Okay, so consider this space x1 which is 0 y belongs to -1 to 1. So basically this red line is basically our x1. And consider this space x2 which is graph of the function sine 1 over x. So this blue line is basically x2. So take the union of x1 and x2, then x is a connected space because both parts of x are connected. So there are two parts of x, and neither of the parts can be written as union of two open sets. So that's why we can say that x is a connected set. Now x is not path connected. So intuitively you can see that if I take a point from x1 and if I take some other point from x2, then there is no path joining this x1 to x2, because no matter how close you get to the origin, you will never reach this line. The graph of x2 will never touch this line, which is basically the y-axis. Okay, so there are some proofs as well of this fact, but we are omitting the proof. So just see this intuitively, that if I take a point, let's say if I take this origin as a point, and if I take some point on the graph of x2, then there is no path connecting this and this. So it is connected but not path connected. Now let's see our next result. If f is a continuous function from space x to y, and x is path connected, then f of x is path connected. So in other words, we can say that continuous image of a path connected space is path connected, or in other words, we can say that path connectedness is a topological property, is a topological invariant. So let's see how to show this result. So this is our space x, which is path connected, and this is our space y, and we have to show that if this is the image f of x, then we have to show that f of x is path connected. So this is our question mark. So of course, if we want to show that f of x is path connected, then take 2 points y1 and y2 from this space. If these are elements of f of x, so there exist points x1 and x2 such that y1 is image of x1 under f and y2 is image of x2 under f. So x is path connected, so there is a path between them. So what we are going to do is we are just going to consider a path. Let's say this is the path h, and take continuous image, or take the image under f of this h, and this will give us a path from y1 to y2. So let's see how to do this mathematically. So we have seen this, f of x1 is y1, f of x2 is y2. Since x is path connected, so there exists a path p from I to x such that p of 0 is x1 and p of 1 is x2. Now consider the path h. Okay, sorry, this is p. Okay, so now we want to construct this h. So this is the question mark. Okay, consider the path h from I to f of x defined as h of t is equal to f of p of t. So basically this is the composition. Okay, so let's see how this h of t is path from y1 to y2. So p is continuous, f is continuous, so that composition is continuous. So that's why h is continuous. So what is h of 0? So the beginning point is h of 0 is f of p of 0. So which means this is equal to f of x1, which means, so what is f of x1? F of x1 is y1. So that's why h of 0 is y1. Similarly, what is h of 1? It is y2. So let's see what is h of 1. So this is equal to f of p of 1. So p of 1 is basically x2. So f of x2, so f of x2 is y2. So that's why we have a function h from I to f of x, which is continuous. H of 0 is y1, h of 1 is y2, so it's a path from y1 to y2. Similarly, given any 2 points of f of x, we can find a path from those 2 points using basically the connectedness of x and the continuity of f. So path connectedness is a topological property, is a topological invariant. So let us analyze path connectedness a little deeper. If x is a space, then the binary relation tilde on x defined by a is related to b if there exists a path in x from a to b is an equivalence relation. Okay, so let's see how to prove that this relation is an equivalence relation. So a relation is equivalence relation if it is reflexive, symmetric, and transitive. So basically I'm just going to give outline of the proof, and it is an exercise for you to fill in the details. So if I have a space X, and if I have a point, let's say A, in this space X, then I need to find a path from A to A. So of course it's a very trivial path. So f from I to X such that f of t is equal to A. So it's a continuous function since it is a constant function. So a continuous function such that f of 0 is A and f of 1 is A. So it is basically path from A to A. So similarly, we have also seen that if I have a path f from I to X from A to B, okay, so let's say f is a path from A to B such that f of 0 is A and f of 1 is B, then now we need to show that A is related to B, then B is related to A. So that's what the symmetric property is. So if A is related to B implies B is related to A. So how to find a path from B to A? We have seen this, so we can find this path g of t is equal to f of 1 minus t. So g of t is a path from B to A. So similarly, we can prove the transitivity. Okay, so if A is related to B, in other words, there is a path from A to B, and B is related to C, so there is a path from B to C, then we have to show that there is a path from A to C. Okay, so I'm going to leave this as an exercise for you. So we can say that path connectedness is an equivalence relation on space X. So the equivalence classes under the above equivalence relation defined from the path connectedness are called path components of X. So the path components of a space X are maximal path connected subspaces. Moreover, every path connected subset of X is contained in the unique path component of X. Okay, so we can say that given any space X, so this space has maximal path connected subspaces which are basically equivalence classes of this path connected equivalence relation. So every path connected subset of X, so let's say this is the space X, and let's say these are the path components of X, and given any path connected subset of X, let's say this is the path connected subset of X, then it must be contained in one of the unique, okay, path components of X. So these are two path components, so any path connected subset of X must be contained in a unique path component of X. So there is a difference. So a path connected subset of X may not be maximal path connected component. So the maximal path connected component is the biggest set which is path connected. Okay, so there may be more than one big set. So for example, this is one path connected component, this is the second path connected component. So there is no set which is bigger than this set which is path connected. So this is the path connected, maximal path connected component. So let's define the functor pi naught using the path connectedness. So let X be a space. We define pi naught of X to be the set of path components of X. So what are the path components of X? So we have already seen that these are basically the equivalence classes of the equivalence relation defined from the path connectedness. If f is a continuous function, then we define the image pi naught of f from pi naught of x to pi naught of y to be the function taking a path component of c of x to a unique path component of y containing f of c. So let's say we have this space X, let's say it has some path components, so let's say it has 3 path components, and we have some space Y, let's say having again 3 path components. So this is the space x, this is the space y. So what does this function do? So first of all, pi naught of x is this set of path components of x. So this is the path component, let's say x1, x2 and x3. So pi naught of x is basically equal to the set x1, x2 and x3. So this is pi naught of x. So similarly in this case, if this is y1, y2 and y3, then pi naught of y is equal to y1, y2 and y3. So this is pi naught of x and this is pi naught of y. And if f is a continuous function from x to y, then we can define what is pi naught of f as well. Okay, so what does this pi naught of f do? So it takes basically a path component of x. So for example, it takes x1 and it takes its image, so f of x1. So now we know that continuous image of a connected set is connected. So the continuous image of x1 under this continuous map f must be connected. So of course it will be contained in one of these 3 components, path connected components of y. So let's say it is contained in y1. Okay, so let's say this is f of x1. So now this is a connected set contained in y. So basically this pi naught of f when applied on x1 will give me y1, because y1 is the unique path connected component of y containing f of x1. Similarly we can find other images. So pi naught f of x2. So once again x2 is path connected component, so in other words it is path connected. So if it is path connected, then continuous image of a path connected space is path connected. So its image, so for example it's contained in this set f3. So this is f of x2. It is path connected subset of y3, so the image will be y3. Similarly pi naught f of x3 can be calculated. So it will be contained in one of these 3 path connected components, and whatever path connected component it is contained in, that will be the image of pi naught of f of x3. So that's how we can calculate pi naught of x, also pi naught of f for any continuous map from x to y. So using these observations, now we are able to define the following functor pi naught. So it's a functor from top, the category of topological spaces, to the category of sets. So in the category of topological spaces, what are the objects? Objects are topological spaces. Morphisms are basically continuous functions, and composition is usual composition. In the category of sets, what are the objects? Objects are the sets. So we can see that if x is any space, any topological space, then pi naught of x is just a set. It is a set containing x1, x2 and x3. So it has 3 elements, and we can see that there is no structure on this set x1, x2, x3. There is no topology, there is no group, there is no other structure on this set pi naught of x. So we can say that this is just a set. Similarly for y, pi naught of y is y1, y2, y3. So we can say that pi naught of y is just a set. Okay, so it's a functor, and we also know that functor not only gives us images of the objects, it also gives us images of the morphisms. So in the category top, the morphisms are continuous functions. So let's see. So we have already seen that how to define pi naught of f if f is a morphism between 2 topological spaces. Okay, so how we define pi naught of f, we have already seen it, and it is just a map from this set pi naught of x to the set pi naught of y. Okay. So the functor pi naught from the category top to the category sets is a covariant functor. Moreover, if f is homotopic to G, then pi naught of f is equal to pi naught of G. Okay. So it's a covariant functor. So we have already seen that how to define pi naught of x if x is any object in the category of topological spaces. So it will give me the path connected components. So we have already seen that what is pi naught of f. So it takes elements, it takes path connected components of x, and it gives me path connected components of y. So from in this case, f is a continuous function from x to y. So since you can observe that f is a function from x to y, then pi naught of f is a basically function from pi naught of x to pi naught of y. So the direction of the arrow is not reversed, it is the same, x to y, pi naught of x to pi naught of y. So we can say that it is covariant functor and not contravariant functor. Okay, so it is a covariant functor. Okay, so similarly we can see that pi naught of f composition G is equal to pi naught of f composition pi naught of G. So in other words, what we are saying is if we have x to y and we have y to z, okay, so G is a function from x to y, f is a function from y to z, then this f composition G is a function from x to z. So what this statement is saying is if you apply first pi of G, so pi naught of x to pi naught of y, and then goes to pi naught of z. So this is pi naught of G, this is pi naught of f. Okay, so this statement is saying that so taking this map from x to z, which is basically first applying G and then applying f. So if we calculate this continuous function, of course if f and g are continuous, then its composition is continuous. So this continuous function from x to z, if we calculate pi naught of f composition G, so it is the same as first composing, okay, so first calculating pi of G, pi naught of G, and then composing it with pi naught of f. Okay, so if we have a connected component in C, okay, so let's say, so a connected component C in X, so this connected component of X, so when we take its continuous image in G, then it will be contained in a unique path connected component of Y. So let's say pi naught of G of C is equal to some path connected component of Y, let's say C prime. Okay, so similarly we can apply f on this C prime, and it will give me some path connected component. So it will give me a path connected subset of Z, and which will be contained in a unique path component of path connected component of Z. So basically you can say that pi naught f of C prime is equal to, let's say, C double prime. So since C is a path connected component, so its continuous image is also path connected. So f composition G when applied on C will give me a path connected subset of Z, so which is contained in the same path connected component C prime. Okay, so we can say that these two functions are equal. So these two functions are equal for each and every path connected component of X, so they are equal. So similarly we can show the properties of the functor, which is that it takes identity to the identity. So for example, if I have an identity map from x to x, so this is the identity of x, then pi naught of 1x. So if it is identity, then of course it takes path connected components of x to itself. So for example, if x has path connected components, let's say x1 up to xn, and this 1x takes elements of x to itself, okay, for all x belongs to capital X. So obviously it takes x1 to x1, x2 to x2, xn to xn. So this pi naught of 1x will take the path connected component xi. So when applied on xi will give me the same path connected component. So in other words, we can say that pi naught of 1x is basically identity function on pi naught of x. So this space is pi naught of x. So these are the path connected components of x. Okay, so this is the identity. So if we write down the identity pi naught of x as this, so this we can say that pi naught of 1x is equal to the identity of pi naught of x. Okay, so next we have to show that if f and g are homotopic, then pi naught of f is equal to pi naught of g. Okay, so if f is homotopic to g, which means that we have a continuous function x cross I to y. So if f and g are continuous function from x to y. Okay, so such that f of x0 is equal to f and f of x1 is equal to g. Okay, so now we have to show that pi naught of f and pi naught of g are equal. So f is a function from x to y, and g is also a function from x to y. So pi naught of f is a function from the path connected components of x to the path connected components of y, and of course pi naught of g is also a function from path connected components of x to the path connected components of y. Now we have to show that if we take a path connected component from pi naught of x, then its image under pi naught of f and pi naught of g is the same. Okay, so let C be a path connected component. Okay, so now we have to show that. Okay, so to show is pi naught f of C is equal to pi naught g of C. Now we know that it's a simple result. So a result that we are going to use, a fact if x and y are path connected, then x cross y is also path connected. Okay, so this implies, so C cross I, where I is basically this closed interval 0 to 1, is path connected. Okay, so since I, which is 0 to 1, is path connected, and we are taking C as a path connected component, which means C is path connected, so C cross I is path connected. Okay, so in other words we can say that the continuous image, so f is a continuous function, so f of C cross I is path connected. So we are not saying that it is path connected component. It may not be the path connected component, but it is path connected because F is continuous and C cross I is path connected. So now what is F of C? So basically F of C is, we know that when we take the value of this second coordinate to be 0, then we get F. So in other words, we can say that F of C is nothing but C cross 0. Okay, so of course which is contained in F of C cross I, which is path connected. Similarly, G of C is equal to F of C cross 1. So why this is the case? Because whenever we take the second coordinate to be 1, then we get the values of G. So we are taking the second coordinate to be 1 here, so of course this is contained in F of C cross I, and F of C cross I is path connected. So in other words, we can say that F of C and G of C are contained in the same path connected set, which is F of C cross I. So if they are contained in the same path connected set, so let's say this is F of C cross I, and let's say this is F of C, and let's say this is G of C. Now this F of C cross I, which is path connected, is contained in a unique path connected component. Okay, so let's say this bigger set is the unique path connected component containing this F of C cross I. So in other words, F of C and G of C are contained in the same path connected component. Okay, so which implies that pi naught of F of C is equal to pi naught of G of C. So basically the continuous image of C under F and G are contained in the same path connected component. So C was any arbitrary path connected component of X, so that's why these two functions, pi naught of F and pi naught of G, are equal from pi naught of X to pi naught of Y. So now we are able to define the functor, and also we have seen its properties. Okay, so now recall that if we have a functor from the category of topological spaces to some algebraic category, for example category of abelian groups or category of groups or category of rings, then we saw that if we have two morphisms F and G, then, and if they are homotopic, then T of F is equal to T of G. And we have also observed that although this functor pi naught is a functor from the category of topological space to the category of sets, and we can say that strictly speaking this the category of sets is not algebraic category, because it doesn't have any algebraic structure like group or abelian group or ring, but still it is preserving this property that if we have two maps which are homotopic, then their images under this functor are equal. So we can say that this functor pi naught is effectively a functor from H top to sets. Okay, so because if F and G are homotopic, then their images are equal, so we don't need to consider extra function, and we just consider its quotient category, which is the homotopy category of topological spaces. Okay, so we know that a connected space may or may not be path connected. So in our next discussion we are going to discuss a condition under which a connected space becomes a path connected space. So for this we need the following definition. So we have to define what is locally path connectedness. So a space X is locally path connected if for each X belongs to capital X and every open neighborhood U of X there is an open set V such that this V is path connected. Okay, so let's say we have a set X. So what we are trying to say that for every X and every neighborhood. Okay, so this is very important. So we shall see in our next examples that this word every neighborhood is very important. So take any neighborhood, then there exists an open set V which is contained in this open neighborhood, such that X is contained in V, which is contained in U, such that this set V is path connected. Okay, so let's consider some example. So a discrete topological space. So what is a discrete topological space? So take X and take topology to be the power set of X. So the power set is basically a collection of all subsets of X. So this is a discrete topological space. Then X is locally path connected. So why X is locally path connected? Because every neighborhood, okay, so let's say X is an element and X is contained in some open neighborhood, then there always exists an open set, that is the singleton, which is contained in U, and this set U is path connected because there is only one point. So there always exists a path from X to itself. So that's why this discrete topological space is locally path connected. So in general, not every path connected space is locally path connected. So let's consider this example. So take this circle S1 and take its union with these sets Xn. So what are these sets Xn? So x0 is 0 1 cross 0. So we are taking y coordinate to be 0 and x coordinate to be from 0 to 1. So in the coordinate plane, this is basically the following set. So this set, so is from 0 to 1. Okay, so this is our x0. So what is xn? So see that we turn a bit using these angles, and we have our t, or in other words the lengths of these vary from n over n plus 1 to 1. So for example, if n is equal to 1, so if n is equal to 1, then this is pi and sine pi, and this becomes t, so which varies from 1 by 2 to 1. So basically our x1 is equal to t cosine pi t sine pi, and t varies from 1 by 2 to 1. Okay, so of course cosine pi is -1 and sine pi is 0, so we can construct this x1, and similarly we can construct other xn's as well. So geometrically speaking, this x, which is s1 union xn's, is basically this circle with some spikes on it. So this this set we have already seen that this is x0, and similarly we can see that these xn will give us spikes kind of objects on the circle. Okay, so now X is path connected. Of course, if I have a set point, let's say this point, and if I have another point, let's say this point, then there exists a path. Okay, so moving along the circle and then moving along this spike. Similarly, if I have another point, let's say this point, and another point, let's say this point, then there exists a path, so moving along the circle and then turning to this spike. So it is path connected. But let's see if it is locally path connected or not. So consider this point, which is the origin 0 0. So the definition of locally path connected says that if I have a point and corresponding to every neighborhood, there exists an open set contained in that neighborhood, which is path connected. Okay, so since it is every neighborhood, so I'm going to take the neighborhood, which is basically a circle of radius 0.2 and centered at 0 0. So I'm going to take this n 0.2 0 0. So if we magnify this circle, so this radius is 0.2 and the center is 0, 0. So this is a neighborhood of the point 0, 0. So now we are going to find an open set which is contained in this neighborhood, which is path connected. Of course, we can't find any open set V which is path connected, because how much closer, okay, so let's say we get much closer to this point, but still it is not path connected because there is no path from this point to this point, for example. Similarly, we can get much more closer and there will be other spikes as well. Of course, we can't show all of the spikes, so there will be some other spikes in this set as well, and we can't find points, a path from this point to, for example, this point. So this neighborhood does not contain an open set which is path connected. So we can say that in general a connected space, a path connected space, may not be locally path connected. Okay, so if X is connected and locally path connected, then X is path connected. So the proof is very simple, and I'm going to leave it as an exercise. So the idea of the proof is very simple. If X is connected and locally path connected, so if X is connected, then there is only one connected component and it is locally path connected. So corresponding to every point, we can find an open set containing that point, such that that open set is path connected. So in general, we can say that X is path connected. So our last topic of today's lecture is deformation retract. So deformation retract is a special case of homotopy. So let's see how we define deformation retract. So let's say we have a space X and A is a subset of X. I is the inclusion map. Then A is deformation retract of X if there is a continuous function R from X to A such that the following conditions hold. So what does the first condition mean? So it means that if I start from some point of A, so A is a point of A, and if I apply R on this thing, then it must be equal to 1A of A. In other words, this means that this is equal to A, so R I of A is equal to A. So in other words, it says that basically if I have, let's say this is the space, and let's say this is some subset A of X, then this condition means that, so when we embed this A into X, then these are the points of X. Okay, so basically we are just saying that these are the same elements of A regarded as elements of X now, and when we apply R on this thing, then we should get A. So in other words, R restricted to A is equal to identity of A. Okay, so I of A is equal to A, but as an element of X, so R of I of A is equal to A. So let's see what does this second condition mean. Okay, so this second condition says that R composed with I is homotopic to identity. So what is this map R composed with I? So we start from X and we reach A, and when we apply A, then we just embed it into X. So in other words, when we apply some point R on some point of X, then we have I of R of X. So this I is just making sure that we are embedding A into X. So in other words, we are regarding A as points of X. Okay, so R of X is a point of A. So in other words, R is taking points of X to A, and A is embedded into X. So the image of this is just A which is contained in X. Okay, so the image of I composition R is basically A contained in X, because this I is making sure that A is embedded into X. Okay, so now this is homotopic. Okay, so I composition R from X to A, which is contained as a subset of X. Okay, so what is the domain of Ix? X, and the range or the image is X. Okay, so now the image of I composition R is A, and the image of I of X is this X. Okay, so in other words, this set X, which is the image of I composition R, is basically continuously deformed into A. So basically at t is equal to 0 we have this thing. So since these are homotopic, okay, so at t is equal to 0 we are at 1x, and at t is equal to 1 we are at I composition R. So at t is equal to 0 we have this whole space X, but with the passage of time, as the time passes from 0 to 1, then at t is equal to 1 we are at A. So the image of this function is A. So basically somehow we are deforming this set A into this set, okay, sorry, we are deforming this set X into this set A. Okay, so we are obtaining this A, and at the end we have this set A at t is equal to 1. Okay, so let's consider some simple shapes. So for example, if I have this planar region, and let's say these are two holes in this region, and this is our region. Okay, so, consider this set. So let's say this is set A. Okay, so this blue is set A, and this red is set, let's say, X. Now we can define a deformation retract. Okay, so how can we define deformation retract from X to A? So at t is equal to basically 0 we have these points of X, and with the passage of time we kind of move, we deform these points to the points of A. Okay, so we deform the points of X to the point basically this subset A of X. So this is deformation retract. So as you can see that it is a special case of homotopy. So in homotopy we do basically the same thing. We have a function f, and we have another function, let's say g, and let's say these are the endpoints. This is f. So we are continuously deforming, so one function into other function. Now in this case we are continuously deforming I composition R to 1x, or the other way around, we are deforming 1x into I composition R. So what is the image of I composition R? It is A. And what is the image of I of X? It is the whole X. So with the passage of time we are starting from X and we are moving towards the points of A. Okay. So to understand more about the relation between homotopy and deformation retract, we need the following definition. So X is a space and A be a subset of X. If function R from X to A is a retract if R of X is equal to A and R restricted to A is identity. Okay, so let's say this is the space X and this is the subset A of X. Then this condition says that R of X is equal to A. So if I take this element and this element, okay, so let's say it is the same space X and let's say this is A. Okay, so if I have this point, let's say A, then its image, this will R of A will be point of this set subset A of X. Similarly, if I have another point, let's say x1, then R of x1 will be an element of A. But also when we take elements from this capital A, let's say if I have an element alpha, then R of alpha is equal to alpha. So it behaves like identity when we restrict this R to this subset A. So it is identity on this subset, and it's taking all other elements of X to the elements of A. So we can rephrase the above definition of deformation retract as the following: let X be a subspace space and A be a subset of X, then A is a deformation retract of X if one X is homotopic to R. So what is this R? It's taking every point of X to the points of A. So basically this is the image of R, and of course we know the image of one X is the whole space X. So they are homotopic. In other words, with the passage of time, each point of X is being retracted, or it's been deformed to the points of A. Or in our other example, it's a planar shape. Okay, so in this case we can take a subset of X to be this subset, and this is deformation retract of this space X, because with the passage of time we can take points of X and continuously deform to the points of A. Okay, so this red is set A and this blue is space X. Okay, so the following result is easy to show. If A is deformation retract of X, then A and X have the same homotopy type. So when we say that two spaces have the same homotopy type, if we have a function from X to A and another function from A to X, such that F composition G is homotopic to 1A and G composition F is homotopic to 1X. Okay, so in this case it's very clear from the definition of the deformation retract. So what's the map from A to X? So the map from A to X is the identity, so I from A, which is embedded into X. And what's the map from X to A? So the map from X to A is X to A, this retract map. Okay, now what about these relation? So let's see what is I composition R. So I composition R should be homotopic to identity of X, so it is from this condition. And similarly, what is R composition I? So this is equal to identity of A, so of course it is homotopic to I of A, because homotopy is reflexive. So if two functions are equal, then of course they are homotopic. So our last example of today's lecture is if S, so S is a circle in plane. So it's a deformation retract of complex plane minus the origin. Okay, so let's say this is our complex plane, and let's say this is the circle, and if we take out this origin, then this whole complex plane is has S1 as a deformation retract. So how to prove this thing? Of course we have to find, or we have to show that this R is homotopig to basically another map, which is basically the identity of X to X. Okay, so 1X, so where X is equal to C minus 0 is the identity from X to X, and we have to show that it is homotopig to this retract. Okay, so we know that every complex number can be written in the following form: z is equal to rho e raised to power iota theta, where rho is greater than 0 and theta varies from 0 to 2 pi. We can define capital F from X cross I to X. So once again, X is equal to C minus 0, such that F of rho e raised to power iota theta t is equal to 1 minus t rho plus t e raised to power iota theta. Now it's easy to observe that this capital F is a continuous function. Now let's see what will happen if I put t is equal to 0. So for t is equal to 0, I will get rho e raised to power iota theta. Okay, so in other words, this is equal to the identity of x, and let's see what will happen if I take the value of t to be 1. So this is equal to, so this becomes 0, and so this is equal to e raised to power iota theta. So what is e raised to power iota theta? So this is equal to cosine theta plus iota sine theta, and these are the points on the unit circle. So why these are the points on the unit circle? Because their magnitude is 1. Cosine square theta plus sine square theta is equal to 1. So that's why these are points on the unit circle S1. So that's why we can say that this is equal to the retract. So take points of the plane and it will give me points of S1. This is the end of the lecture. Thank you very much, and Allah Hafiz.